Welcome to Brain Vision.
For this problem on the topic of conservation of energy, we are given a horizontal spring that is attached to a wall with a given force constant. Attached to the spring is a block with a given mass which rests on a frictionless horizontal surface as in the figure. We are given the position that the block is pulled from equilibrium before it is released. We want to find the elastic potential energy stored in the spring at a given distance from equilibrium and then when the block passes through equilibrium. We also want to find the speed of the block as it passes through the equilibrium point and the speed of the block when the equilibrium position is halved. We want to know why the answer also to part C is not half the answer to part B. So firstly, we have to calculate the energy stored in the spring, and this is the elastic potential energy. So the elastic potential energy U is equal to a half kx squared. Now we are given the force constant K, and at x is equal to 6 centimeters, we can calculate this elastic potential energy. So this is equal to a half times the force constant of 850 newtons per meter, and we want to calculate this elastic potential energy at 0.06 meters from the equilibrium position, so that's x, and that's squared. So we get the elastic potential energy at 6 centimeters from the equilibrium position to be 1.53 joules. That's our first answer. Now, for part B, before we do part B, we actually want to find the elastic potential energy U when x is equal to 0, so when the block passes through the equilibrium position. Now we know at the equilibrium position x is equal to 0, and hence a half kx squared is equal to 0. So the elastic potential energy to the equilibrium point is 0 joules. Now we can move on to question B. In question B, we want to find the speed of the block as it passes through the equilibrium point. So we know we have to apply the conservation of energy. So all of the initial elastic potential energy stored in the spring is converted to kinetic energy through the equilibrium point. So the change in kinetic energy plus the change in potential energy is equal to 0. Meaning that at the equilibrium point, the kinetic energy of the block are half mvf squared, where vf is its speed through the equilibrium position, minus its initial kinetic energy, a half mvi squared, plus the change in potential energy uf through the equilibrium position, minus the elastic potential energy initially ui is equal to 0. Now the final kinetic energy of the block is that through the equilibrium position, a half mvf squared. Now vf is what we want to find, the speed of the block through the equilibrium position. Its initial kinetic energy is 0 since it starts from rest, and this is equal to minus uf minus ui, the change in elastic potential energy. So a half mvf squared is equal to ui minus uf. So essentially, we know uf is equal to 0. So to the equilibrium position, there is no elastic potential energy. So we have, if we rearrange, we get vf to be the square root of 2 times ui over m, where m is the mass of the block. And we have these values, so we can substitute them in. So that's the square root of 2 times 1.53 joules. So all of the 1.53 joules that is initially stored as elastic potential energy is then converted to kinetic energy through the equilibrium point. And this is divided by the mass of the block, 1 kg. So calculating, we get the speed of the block to the equilibrium position to be 1.75 meters per second. Now, next, we want to find the speed of the block when it's at a position of half of the initial position, 6 centimeters, so xi over 2. So again, we'll use the equation for the elastic potential energy at this point, which is not 0, a half kx squared, to be a half times the force constant of the spring, 850 newtons per meter, at a distance of 0.03 meters from equilibrium, and that's squared. So the elastic potential energy at this point is 0.383 joules. And again, we need to find the kinetic energy so we can find the speed. Now from above, we saw that a half mvf squared, where vf is now the speed through the point that is 0.03 meters from the equilibrium point, must equal to ui minus uf, the change in elastic potential energy. So therefore, the speed that we're looking for, vf, is equal to the square root of 2 into ui minus uf all over the mass of the block m. And now we can put our values into this and solve for this speed. So that's the square root of 2 into 1 point. So the initial elastic potential energy is 1.53 joules minus 0.383 joules divided by the mass of the block, which is 1 kg. And so solving, we get the speed of the block at this point to be 1.51 meters per second. And lastly, we want to know why the answer in C is not half the answer in B, since we halved the distance that the block has moved. Well, remember that the energy is proportional to the square of the distance, and the energy is not proportional to the distance itself. If it were, then the speed would be halved.